Hello and welcome back. In this series of lectures, we are talking about the properties of discrete time Fourier transform. In the previous lecture, we had seen the properties of linearity, time reversal, linearity, then periodicity, and in the just now we had seen about time shifting property. In this lecture, we will be talking about the frequency shifting property. Now, this frequency shifting property is a dual of time shifting property. Now, what will happen if we shift the spectra in the frequency domain? That is, if DTFT of a signal is shifted in frequency, there is a frequency shift. Okay, what will happen to the time domain signal then? Okay, so it is a dual property. In the previous case, it was seen that when we are shifting the signal in the time domain, the frequency domain spectra was getting multiplied by e raised to minus j omega k. Here, when we are shifting the spectra in the frequency domain, the time domain signal is getting multiplied by the exponential term. So here it is minus omega 0, but here it is omega 0. Okay, so this sign you have to remember. Okay, so this is this can be denoted directly by like this. Okay, this is shift in the frequency domain. So shift in the frequency is domain is characterized by multiplication of e raised to j term in the x domain, in the time domain. Now this can be proved easily. Now you can find out the Fourier transform of e raised to j omega and substitute in the standard equation. Now you can combine these two exponentials with the single exponential, and now this whole equation is nothing but our x e raised to j omega minus omega 0, that is the DTFT. So this proves that the Fourier transform of e raised to j omega 0 n will be the frequency shifted version of x omega, that is original discrete time Fourier transform. So this is called as the frequency shifting property. Next is the time reversal property. What will happen if we reverse the signal in the time domain? What will happen if we take the mirror image of the signal in the time domain? So it says that when we take the Fourier transform of the time reversed signal, then the spectra also gets time reversed. Okay, so the spectra is also getting phase reversed. So what is actually happening here? Instead of e raised to j omega term, we will get e raised to minus j omega term. Okay, this is called as the phase reversal. Phase spectrum undergoes a change leading to the phase reversal. So time reversal is leading to phase reversal in the frequency domain. So time reversal in the time domain is leading to phase reversal in the frequency domain. So you have to understand this relationship of time and phase. Okay, there is a relationship between time and phase. So when we are reversing the time in the time domain, there is phase reversal occurring in the frequency domain. How to prove this? So we have to take the, by definition, the Fourier transform of x of minus j omega, x of minus n. So substitute this in our standard equation. This equation is the standard equation of DTFT. Now we can do this substitution. Let us substitute minus n is equal to m. Then follow the standard procedure. Let us change the limits now from n to m. Let us change these limits from n to m. So to change these limits from n to m, we do the substitution. When n tends to minus infinity, minus of minus will become plus. So m will tend to infinity. When n tends to infinity, m will tend to minus infinity. So after substituting this in the standard equation here, we will get that we can write this e raised to minus j. Since here in this our standard equation we want here minus. Okay, so that's why we make this arrangement. We take minus here, and instead of omega here it will be minus omega m. And now we can write the standard equation, that is x, the Fourier transform of x of minus n will be x e raised to minus j omega. So this shows that the time reversal leads to phase reversal in the frequency domain. Just like the other properties which we had studied for different Fourier transform, the same property is here, differentiation property, which we had seen in the Z transform also. So differentiation property, what does it state? It states that if we take the derivative of the frequency spectra, then the time domain signal gets multiplied by n. So this is an important thing. There also it was getting multiplied by z in the Z transform. Okay, so now if you use the definition of x e raised to j omega, Okay, now instead of having the Fourier transform of x of n, let us try to have the Fourier transform of nx of n. Let us try to prove from the LHS. So first we try to take from the LHS, we have to reach this as RHS. Now if you use our standard equation of DTFT and find out the Fourier transform of n into x of n, then we can write this formula like this. So we can make the substitution here. Next, now let us take the derivative of this x e raised to j omega. So what will be the derivative of the DTFT? Now if you take the derivative, if you have to take the derivative with respect to omega here, so this is our omega variable d by d omega. If you take the derivative of d by d omega of e raised to minus j omega, you will get minus jn, and the derivative of this will be same. Okay, because here n is constant, so e raised to minus jn, e raised to minus j omega. Now this is the derivative. So after taking this derivative, now this is minus j, so if you take on the LHS, it will become plus j. So this minus sign will become plus here, so this is plus here, and now this is our derivative is there, our derivative is there on the right hand side, derivative is there on the left hand side. Now we get this. Now if you see this equation, what does this equation mean? This equation means it is the Fourier transform of n into x of n. So hence we have proved the property, that is, if you take the Fourier transform of n into x of n, you will get j into d by d omega of x e raised to j omega. That is, a differentiation of the DTFT in the frequency domain leads to multiplication of the time domain signal by n, by a factor of n. Next is the convolution property. Convolution property is a very important property for all the transforms. What does convolution property state? That convolution property states that when we are convolving the signals in the time domain, then in the frequency domain, actually we are multiplying the spectra of those signals in the frequency domain. That is, convolution in time domain is multiplication in frequency domain. This is the universal statement. For this is satisfied by all the transforms. So convolution in time domain is multiplication in frequency domain. So you can see your symbol, convolution symbol in the time domain, convolution of two signals in the time domain is multiplication. So it is your dot, nothing means it dot. So multiplication of two signals in the frequency domain. There is a lot of difference between convolution and multiplication operations. These operations are different. Okay, convolution operation is shown by asterisk symbol, and multiplication symbol in signal systems is shown by dot. Okay, now we can go ahead for proving this property. So this is the definition. By definition, DTFT is given for x of n signal. Now if you use the convolution equation, okay, we know the convolution equation. If you use the convolution equation which we had seen in the second unit, and now substitute in our DTFT equation, we can get this equation here. Now we can apply the time shifting property which we have just studied in this series. So when you apply the time shifting property, so I can multiply this x2 e raised to j omega by simply e raised to minus j omega k, because it is shifted by k samples. Now after substituting this in this equation, okay, you can get here x2 e raised to j omega, and this is nothing but your x1 e raised to j omega. So what does this mean? This means that when you take the convolution of the two signals in the time domain, we are getting actually the multiplication of the two signals in the frequency domain. The spectra get multiplied in the frequency domain. So this is the property of convolution property of Fourier transform, or the convolution property of discrete time Fourier transform. So in this way, we see that the DTFT satisfies the different properties. Just like the Z transform, it has so many properties, right from linearity, time shifting, frequency shifting, then differentiation property, then we had the convolution property, and so on. So all these properties will be helpful for solving the numericals, and these properties will help us to make our task simpler. Okay, so in the next lecture we will be talking about how to solve different numericals of discrete time Fourier transform. Thank you.